So this is the flipped lesson for trig integrals. And right now our ability to integrate trig functions really relies on formula and nothing beyond that. So we're pretty limited. So we're going to add a technique in this section. We're doing a substitution, again, not a use substitution, but we're going to be making some substitutions, or basically rewriting integrals using trig identities, specifically the Pythagorean identities and the half angles formulas. So right now, for example, if I gave you a problem like this, sine to the fifth of x dx, just recognize that this is the same thing as sine of x raised to the fifth power dx, and you really can't integrate it at this point. You would try a use substitution, but it doesn't get you anywhere. So we need something else to help us move beyond that. What if I gave you a problem that looked like this, a product now of powers? And again, you would try and do some sort of use substitution, but you would quickly find out that it doesn't get you anywhere. So we need to further our techniques with trig functions. So the first thing I want to talk about is integrating powers of sine x and cosine x. So when you have an integral in the form, this general form, there's basically two ways that we're going to approach it. And one is we're going to rely on the Pythagorean identities and also the half angle formulas to rewrite the integrals. Now, I know, just an aside, everyone pretty much remembers cosine squared x plus sine squared x equals 1. But the second one, over teaching this course many times, I've seen this get mixed up. So I just want to show you, if you divide everything through by cosine squared, you will get the second Pythagorean identity. This is just 1 plus tangent squared x, which equals secant squared x. So hopefully that will help you to remember both of those identities, of which we're going to be using them quite frequently. So what's going to happen when we want to integrate powers of these functions? So if you have an even or an odd power of sine or cosine, we're going to be doing different things. So let me lay out case 1. I'll call it case 1. So case 1 is where n or m is odd for cosine or sine, okay? And what you're first going to do is split off a single factor. You're gonna split off a single factor. So for example, if I had the integral, let's see, cosine cubed x, oops, that's a 3, dx. I'm going to rewrite this and split off one of the cosines. And then I'm going to replace the even powers with the Pythagorean identity. So I want to replace the even powers with the Pythagorean identity. So this is going to look like 1 minus sine squared cosine x dx. And why did we do that? Well, we want to get a mix of sines and cosines, because now we can do a use substitution. Right? If we let u equal sine x, then du would knock off the factor that we split out. So let u equal sine of x, and then du is equal to cosine of x dx. So now we've taken an integral that we could do nothing with and use u substitution on. So this is simply 1 minus u squared and du. And we know how to deal with that. It's just the power rule. So that's case 1. Case 2 is when we've got an even power of sines or cosines. Okay? And there we're gonna go straight to using our half angle formulas. So for case 2, we're going to use half angles. So if I've got an integral cosine squared x dx, picking on cosine, we're going to make the substitution and rewrite it. And the half angle formula for cosine squared is simply 1 plus cosine of 2 theta over 2, which is just 1/2 1 plus cosine of 2 theta. And now we can just do a u substitution on this and integrate that directly. So we've taken a rather difficult looking integral and we've rewritten it in terms of we've rewritten it using the trig identities in order to take advantage of u substitution. I'm going to pause here for a minute. A natural progression of this, of working with trig integrals, is to actually take products of powers of sines and cosines. So now our general form is going to look like this, right? We're going to have an integral of sine raised to some power m times cosine raised to some power n, and we're asked to integrate it. So here it's going to again depend on whether m or n is even or odd, and I'll give you a little attack plan for that, and then we'll do some problems. So first, if m is odd, right, this is case 1. If m is odd, so in other words sine is odd, then you're going to follow the procedure. You're going to split off one of the sines, replace the even powers with sine, replace the even powers of sine of x with 1 minus cosine x, and then go to u substitution. All right, so we're going to rewrite the remaining even powers and go to u substitution. I'll do a quick example for this one and then lay out the rest of them and we'll do some problems. So for instance, if you had the integral, I don't know, sine cubed x cosine squared x dx. Again, split off one of these sines and you're left with sine squared x, sine x, cosine squared x. And replace the even powers of sine squared with the trig identity, Pythagorean identity, and you get 1 minus cosine squared x, sine x, and cosine squared x dx. So now if I let u equal cosine of x, I can rewrite this integral and use the straight up power rule with it. And du is minus sine of x dx. And hopefully you see where we're going. We're getting an integral now that looks like this, and we can straight up handle that. So if m is odd, in other words the sign is odd, you're going to split them off, okay, and follow the procedure basically that we laid out on the prior slide. If n is odd, in other words cosine's odd, then you're going to split off a cosine and replace the even powers. So if cosine is odd now, you're going to split off one of the cosines and then write the even remaining powers of cosine in terms of sine. And again, go through this process and use u substitution. So that's pretty straightforward. And then if you've got the case where m and n are even, you're going to use half angles, and we'll do a substitution directly. Now that may require multiple iterations, okay? But let's look at a couple examples, and we'll do more in class. That's the whole purpose of the flip, to just work on problems. So I return to the front page, and I just want to go through an example of products of powers of sine and cosine. So here we have powers that are both even, so we're going to go straight to half angles. So they're both even, and we're going to use half angles. Okay, so rewriting these in terms of the half angle formulas, it's just 1 minus cosine of 2 theta, or 2x, I'm sorry, this is in terms of x, 2x divided by 2 times 1 plus cosine of 2x divided by 2. So this is the equivalent of d and dx. I'm just going to pull out the 1/4, and I'm left with a little bit of algebra to do. you're going to have to FOIL this out. Running off the page there. Right, so let's FOIL that out, and I get 1/4 the integral. And if I'm FOILing correctly, I'm going to get 1 plus cosine of 2x minus cosine of 2x minus cosine of 2x squared dx. Okay, so these two terms are going to cancel out. And I'm left with the integral 1/4 1 minus cosine squared 2x. And you may say to yourself, well, gee, I didn't I didn't get any better here, but you really have. All right, hang with me for a minute. So now I can use a trig substitution on that for the Pythagorean identity. So this is the same thing as 1/4 the integral, right? This should look familiar to you. That's just sine squared 2x dx. Okay, so that's helpful, but I'm still not quite there. Well, I can make another half angle substitution. So this is the same thing as 1/4. I'm going to make another half angle substitution. But now, remember, your argument is 2x, so if I make the substitution, that's going to be 4x divided by 2 dx. Now, finally, I'm at a state where I can actually integrate this. Right? And, you know, you can do a u substitution on here. Right, so I'll let u equal 4x, du equals 4 dx. So I have to multiply by 1/4, right? So I'm left with, in this case, I'm left with, pause here for a minute, sorry, children. Okay, so coming down here, I'm left with 1/8. Taking the antiderivative of 1 is just x, and then the antiderivative of cosine 4x when I do a u sub is just 1/4 times cosine, right, the integral cosine of u du, and this is just 1/8 x minus 1/32 sine of 4x plus a constant. So we were able to integrate a rather complex looking integral using half angles and come up with an answer. So I want to finish off this video and point out that we can still use the same kind of concept if we had products of tangent and secant. So here's the general form of the integrals that we would be working on. We'd have the integral of tangent raised to some n power times secant raised to some n power. And the process is very similar. If n is even, right, in other words, the secant term is even, then the power is even. Then we're going to split off secant squared now so that we can utilize the other Pythagorean identity. So we're going to rewrite the remaining powers of secant squared as 1 plus tangent squared, right? And I'll show you an example of that. And then we're going to use a u substitution where we let u equal tangent of x. If m is odd, these are a lot of rules, and it really is just going to take a lot of practice, which is why I wanted to flip this portion. So if m is odd, in other words, the tangent term is odd, you're going to split off a secant x tangent x. You're going to split off a product and rewrite the remaining powers, the remaining even powers in terms of secant squared x minus 1, right? So we're going to rewrite the remaining even powers of tangent of x as secant squared minus x, and then we're going to use the u substitution of u equals secant x. If they're both, if one is even and one is odd, then we're going to, and I am not going to be asked, I just want to make sure you know that this is how you would do it. I won't be going through many examples, or I don't even think I did in a single example of this. where you've got an even and an odd, then we'd rewrite the even powers of x in terms of secant x, and then we would apply reduction formulas, which I do present briefly, but these are the two cases that I'm going to be concentrating on because they're pretty straightforward in their technique. So I'm going to pause and grab an example and return to the front of the presentation. So in this example, I just want to use our rules for powers of secant. Let's start there before we start to look at products. And this is a pretty straightforward problem. So you've got, and I wanted to do a definite integral. You've got the definite integral from 0 to pi over 4 secant raised to the 4th d theta. So you've got an even power. So you're going to split off an even power. And then you're going to use the Pythagorean identity to help you rewrite it. So this is 1 plus tangent squared theta secant squared theta d theta. We're going to let u equal tangent of theta, because the derivative of that is going to give us exactly what we need to knock off, which is secant squared theta d theta. So I can rewrite this integral now and use the power rule, which is so much easier, right? Which is fine, but we just have to make sure we have our limits in terms of u then. So this is taking the antiderivative. You get u plus u cubed over 3. And now I'm going to evaluate tangent of 0, which is simply 0, and tangent of pi over 4, right, because that's what u is. Tangent of pi over 4 is 1. So this is just 1 plus 1/3, which is equal to 4/3. So I think I'd like to stop the video there. We're going to do problems in class, and this is going to be one of those sections where you're going to be revisiting this, and you really need to practice this quite a bit to get familiar with what you need to do. I know there was a lot of information in this video, so again, we'll start out by doing a quick overview, but we're going to go right to problems since they take so much time.